Welcome to Physics Uncomplicated. Sit back, relax, and enjoy as you learn the key concepts of physics. Each chapter in this series is intentionally kept to a maximum of 12 minutes to convey only the essential facts and ideas for that particular topic. You may use these videos as a supplementary aid to refresh your understanding of the chapter. Wishing you all the best.
Before we start our chapter, let's take a moment to introduce the characters who will appear throughout this animated series in both the Class 11 and 12 videos.
Look at the bird above. It doesn't always fly straight, does it?
Exactly. Let's ask Professor. He always makes these concepts easy.
Welcome, class. Today, let's learn about motion in a plane. Let's begin the chapter by examining a few examples. A basketball being passed through the net. A car navigating a turn. Any body moving in two directions simultaneously is said to be traveling in a plane. Before we go further, let's understand the concept of scalars and vectors. Imagine a boy running at a speed of 8 kilometers per hour. In this case, speed is considered a scalar quantity as we do not indicate where the boy is running. When a boy walks toward the east at a specific speed, he has a scalar quantity with direction, transforming it into a vector. Now that we understand the difference between scalars and vectors, let's move on to the next topic. Operations on vectors. Let's assume a car moves north for 5 meters and then east for 2 meters. We can find the total displacement of the car from the starting point using a principle called the triangle law of vector addition. To understand this more clearly, let's visualize this on a graph. Initially, the car moves 5 meters north. Graphically, let this vector be called A. Then, it makes a right turn and moves an additional 2 meters due east. We will refer to this vector as B. To find the net displacement from point A to point B, we draw an arrow that connects the initial and final positions. Let's call this resultant vector R. So in this case, we can say that R equals A plus B. Let's revisit our sports car example and take a closer look at its motion. The car initially moves north, then turns east, and subsequently turns south as it continues its journey. By plotting these movements on a graph, we can visualize the vectors. To find the resultant vector, we connect the initial and final points with an arrow, forming a polygon. Assume the car moved 5 meters in direction A, then 2 meters in direction B, and finally 5 meters in direction C. To find the resultant vector, we need to add the vectors A, B, and C. Let's break this down step by step using vector addition to find the resultant displacement. Vector A can be represented as 0x plus 5y, as the car is moving in positive y direction. Then, vector B can be defined as 2x plus 0y, as the car is moving in a positive x direction. And finally, vector C can be represented as 0x minus 5y, as it's moving in negative y direction. Adding all the x components, we get Rx as 2, and adding all the y components, we get Ry as 0. So the net resultant is given by r equals rx plus ry, which is 2 meters due east. A motorboat is racing north at 40 kilometers per hour, and the water current in that region flows at 15 kilometers per hour in the direction of 60 degrees east of south. Let's calculate the resultant velocity of the boat. Let's solve this step by step using vector addition. The boat is moving in positive y direction only, so the velocity components along x and y axis can be represented as vbx equals 0 and vby equals 40. And velocity of water current equals 15 kilometers per hour at an angle of 60 degrees east of south. Let's resolve the velocity of water current into x and y components and call them vwx and vwy. We can find the values of vwx and vwy by using law of sines and cosines. Vwx equals 15 into sine of 60 degrees, and vwy is negative 15 into cosine of 60 degrees. Please note, as y is in negative direction, we have considered 15 as minus. Adding x and y components of both the boat and water current, we get x component as 12.99 and y component as 32.5. To find resultant velocity, we square root the squares of x and y components. So the resultant velocity is 35 kilometers per hour. To find the direction of velocity, we use the formula tangent inverse of x by y component, which gives us 21.8 degrees. Projectile motion describes the curved path an object takes when it is thrown or launched into the air, with gravity being the only force acting on it after launch. To easily visualize the components of velocity, acceleration, and position acting on the projectile motion, let's break down the components into two, x component and y component. Previously, when we studied motion in one dimension, we learned SUVAT equations. From these, let's evaluate the position, velocity, and acceleration acting on the projectile. The velocity u is the initial velocity, and the projectile is launched at an angle theta to x. Let's begin by resolving the initial velocity u into its x and y components. By drawing a line perpendicular to the x-axis and connecting it to u, we form a right-angled triangle. In this triangle, the hypotenuse is u. From trigonometry, we know that for a right-angled triangle, the sine of an angle, theta, is the length of the opposite side divided by the length of the hypotenuse, while the cosine of the angle is the length of the adjacent side divided by the length of the hypotenuse. So we get initial velocity in x direction as u cos theta and in y direction as u sine theta. Having understood this, let's start writing down the components of acceleration, velocity, and position on the x and y axes. Firstly, regarding acceleration, since there is no acceleration on the x-axis, the acceleration a is equal to 0 on the x-axis. However, the projectile experiences an acceleration due to gravity in the negative y direction, so we have a equals negative g. Next, let's discuss velocity. For this, we'll use the first SUVAT equation, which states that v equals u plus at. Since acceleration is equal to 0 in the x direction, we can express the velocity in the x direction as v equals ux. we know that ux equals u cosine theta. In the y direction, substituting the acceleration as negative g, we get the velocity component as u sine theta minus gt. Lastly, let's find the position of the projectile with respect to time. From the last Suvat equation, we know that s equals ut plus 1/2 at squared. Substituting this for both the x and y coordinates, we obtain for the x coordinate, x equals u cosine theta into t. For the y coordinate, y equals u sine theta into t minus 1/2 gt squared.